Okay, it's time to move on. In the last class, we have begun to look at real-world one-dimensional extended solids. And the first extended solid we looked at was the polyacetylene. And now I would like to discuss another example, which is a little bit more complex than the previous example, which is called the Krogmann's salt. So Krogmann's salt is a pretty simple but fascinating compound, both from aspects of chemical bonding, but also from the property aspects. So Krogmann's salt is nothing else but potassium tetrachloroplatinate. You can make it very easily from platinum nitrate and potassium cyanide in aqueous solutions. So under those conditions, the cyano ligands, they coordinate to platinum. So platinum is a D8 species. It's because it's in the oxidation state 2+. So for that reason, it adopts a square planar shape. So you have overall four cyano groups that surround the platinum in a square planar fashion. So that complex anion has overall a 2- charge because the four negative charges of the cyano groups and the two positive charges at the platinum. So potassium is then simply the countercation to that complex anion. So you can crystallize that compound from a solution, and it makes a quite interesting crystal structure. It actually forms, well, one-dimensional infinite chains of the tetrachloroplatinate anions. You see here two different perspectives on these one-dimensional chains. You see that the platinum atoms are stacked in one dimension, whereas the PTCN4 units, they are oriented in a near eclipsed fashion, okay, along a chain. So it's not ideally eclipsed, but the bond angle is very small, so it's almost eclipsed. Okay, so you have these one-dimensional chains in your crystal structure, and then in the space in between these one-dimensional chains, you have your potassium atoms. These are these white balls. These white balls here. All right, now you can look at the distance between the platinum atoms, and that's about 3.48 angstroms. So that's a relatively long platinum-platinum distance, which suggests that there may be some minor bonding interactions in between the platinum atoms, but overall they must be pretty weak. So when you look at the electrical conductivity of that compound, then you will find that it's practically an insulator. So the conductivity is very low. It's 5 times 10 to the minus 7 Siemens per centimeter, or 5 times 10 to the minus 7 1/ohm times centimeter to the power of -1. All right. So in this view, we would say that, well, these platinum atoms, okay, which are stacked in one dimension, they would not be considered to be, well, a one-dimensional electrically conducting wire of platinum atoms. However, this changes dramatically when you oxidize that salt with a little bit of bromine. Okay, so when you add bromine to that salt, then and you recrystallize that salt, then it recrystallizes with some bromide ions in the crystal structure, and the crystals have overall the composition K2 PTCN4 Br times 3H2O, which means that you now have also 3 hydrate water molecules in the crystal. So that would also imply that, well, the oxidation state of platinum must now be somewhat higher than +2. It must be in between +2 and +3 due to the presence of the additional bromide ions in the crystal structure. So now you can look at the crystal structure again, and you see that there are some similarities to the previous crystal structure, but there are also significant changes. So like previously, you have again one-dimensional hydrogen, one-dimensional chains of tetracyanoplatinate anions, which are square planar. Okay, so now see the C again. But in contrast to the non-oxidized form, the PTCN4 units are now in a staggered conformation. And when you analyze the platinum-platinum distances, then you see that they are now significantly shorter. They are now only 2.88 angstroms. Okay, so now this suggests that there may really be significant platinum-platinum interactions now, because there is the correlation between bond length and bond strength. The shorter the bond, the stronger the bond. Now we have a significantly shorter bond, and that means, well, that the platinum-platinum bonds must be significantly stronger now. Now, because of these shorter distances, there is more steric repulsion between the cyanoligands, explaining now why the PTCN4 units are oriented in a staggered conformation and not anymore in an eclipse conformation. Okay. Now, when you analyze the electrical conductivity now, then you all of a sudden find that your compound is a quite good electrical conductor. Your conductivity is now 200 Siemens per centimeter. Okay, so your conductivity is basically 9 orders of magnitude higher than it was previously. But this conductivity occurs only in one dimension. Okay, it actually, when you have a Krogmann salt single crystal, you will find that the electrical conductivity exists only in the direction of the one-dimensional chain of PTCN4 units. In any other, the other 2 dimension, you will not find a significant conductivity. So this means that your compound, the Krogmann salt, is a one-dimensional conductor. Okay, it conducts in one dimension of the crystal, but not in the second and in the third dimension. So Because of that, you can actually now say with good justification that we have a one-dimensional chain of platinum atoms that form something like a platinum wire to the crystal. So how can we explain this behavior using band theory? So let us construct the band diagram first for the non-oxidized version of the Krogmann salt, and after that for the oxidized version of Krogmann salt, and see if we can explain this metallic behavior of the oxidized form. Okay, in order to do this, let us make one simplification. Let us, in a thought experiment, substitute the cyanoligands by more simple hydridoligands that would form a one-dimensional PTH4 2- chain. All right. Now, if we want to develop the band structure for this chain, we first need to be clear which orbitals we want to use in order to construct the chain from which then the band is derived. So in order to select the orbitals, we first must produce the molecular orbital diagram for an individual PTH4 2- unit. Okay, now let's do this, and we can now use our molecular orbital diagram construction skills and our symmetry adapted linear combination of atomic orbital skills. Okay, so clearly the platinum atom would be the central atom orbital, and the 4 hydrogen atoms would be the ligand orbitals. Okay, we would look at the ligand orbitals first, and well, because we have 4 hydrogen atoms, we would expect that we would form 4 ligand group orbitals. Okay, so in order to produce them, we would first need to determine the reducible representation for these ligand group orbitals, and then from that, using the reduction formula, calculate the irreducible representations for these ligand group orbitals. So I'm not going to the explicit calculations here. I'm just presenting you the outcome. So the outcome is that we have one ligand group orbital that has A1G symmetry, 2 ligand group orbitals that have EU symmetry, and one more ligand group orbital which has B1G symmetry. So these ligand group orbitals are depicted here. So this A1G ligand group orbital does not have a node. As you can see, all the 1s orbitals have the same algebraic sign. So the 2 EU orbitals, they have 1 node. They are double degenerate. You see the first one has its node here, and the second one has its node, over there. Okay, so these 2 orbitals are just 90-degree rotations relative to each other. So the B1G ligand group is the one with the largest number of nodes. It has 2 nodes, so there's 1 node here and 1 node here. Okay, so what's the next step? The next step is to determine the symmetry types of the central atom orbitals. Okay, so in this case we have platinum. That means that we have the d orbitals to consider, in particular the 5d orbitals, yeah, but we also have the 6s orbitals to consider, which are being full, as well as the 6p orbitals to consider. So you would have to find the symmetry types for all these orbitals. Now to do this, you just need to look into the character table. So certainly the 5s orbital would have A1G symmetry. Okay, so the PZ orbital would have this symmetry here, which is A2U. The PX and the PY orbitals would have EU symmetry. And the symmetry of the d orbitals would be B1G for the dx square minus y square, B2G for the dxy, EG for the dxz and the dyz, and A1G for the dz square, because z square appears here. All right, so you see here the result, A1G for the S, B2G for the dxy, EG for the dyz and the dxz, EU for px and py, A2U for pz, A1G for the dx square minus y square, and B1G for the dx square minus y square. All right, now we are in the position to construct our molecular orbital diagram. Everything is like in the previous examples that we have discussed so far. It's just getting a little bit more complicated, but the concept is the same. So now here on the left side, you have the 5D, the 6S, and the 6P of the platinum in relative energies. So here on the right-hand side, we have the 4 LGOs for the hydrogen. Okay, so you see here again all the symmetry types of the atomic orbitals and the ligand group orbitals respectively. Now our task is just to combine platinum orbitals and ligand group orbitals of the same symmetry type to form molecular orbitals. Okay, so now we can, for instance, start with the A1G orbitals. So the 6s has A1G symmetry. We find that one of the 5d orbitals also has A1G symmetry. Now you see that one ligand group orbital has A1G symmetry as well. So that means that these three can be combined to form molecular orbitals. Okay, one bonding one anti-bonding one, and one approximately non-bonding one. Okay, you see the bonding one here, which has low energy. You see the anti-bonding one here, and you see the non-bonding one here in the middle at intermediate energy. Okay, so next you can, for instance, look at, well, the B1G orbitals. So one of the d orbitals has B1G symmetry. You see there's one ligand group orbital that has B1G symmetry. Well, that produces overall 2 molecular orbitals. Well, this bonding molecular orbital here, which is B1G, and you see an anti-bonding molecular orbital here, which is B1G symmetry. Okay, next you can go, for instance, to B2G symmetry. You see that this 5D orbital has B2G symmetry. You see now there's no ligand group orbital that has B2G symmetry, and that means that this 5D orbital remains non-bonding, and you write it with the same energy into the molecular orbital diagram. Okay. So next you can, for instance, pick these EG orbitals, of which there are two. There are no other EG orbitals. We don't have EG ligand group orbitals, so therefore these EG orbitals here also remain non-bonding. Okay? You write them with the same energy into the molecular orbital diagram. So what's left? Well, we haven't looked yet at the A2U and the EU orbitals for the 6p orbitals. Among those, we find that the EU orbitals can interact with the EU ligand group orbitals. Okay, now because of the double degeneracy, we form two bonding molecular orbitals that have EU symmetry and two interbonding molecular orbitals that have EU symmetry. Okay, so the A2U orbitals, that A2U orbital, it doesn't find a partner, and it's written non-bonding into the molecular orbital diagram. So last but not least, we still need to fill in the electrons. So how many electrons do we have? So the platinum is platinum 2 plus. Therefore, that's a D8 species. Okay. Consider that platinum is in the group 10 within the periodic table, has 10 valence electrons, and the oxidation state plus 2 electrons are being removed. Okay, so 8 electrons are being left, and these 8 electrons are in 4 of the d orbitals. All right, so now the ligand orbitals are considered completely full because we consider our ligand as a 2-electron donor. Okay, that makes a dative bond to the platinum. So for that reason, our hydrogens are considered to be hydrido ligands, H- ligands. Okay? Therefore, each hydrogen has 2 electrons, giving 8 electrons overall. So 8 plus 8, that gives 16. And now we have to fill these 16 electrons into the most bonding molecular orbitals under the consideration of the Pauli principle. So that means that this orbital here gets full, this orbital gets filled, that orbital gets filled. You see that these are 4 bonding molecular orbitals, which can explain the 4 platinum hydrogen bonds. But now you see that another 8 electrons are left, and these 8 electrons you have to fill now into these 4 approximately non-bonding orbitals. So these 3 orbitals here are actually exactly non-bonding. This A1G we said is approximately non-bonded. Okay. So now these 3 orbitals, they exactly resemble the dxy, the dxz, and the 3 yz orbitals of the metal. Okay. These 2 orbitals can be approximated as the d square orbital of the metal and the dx square minus y square orbital of the metal. That is so because this one has been constructed from the dz square and has an energy fairly similar to the dz square. So it has little influence from the ligand group orbital. Therefore, in good approximation, we can say that this orbital still closely resembles our dz square orbital. Okay? And for this orbital here, which is interbonding, we can say that well, it still reasonably closely resembles the dx square minus y square orbital because it has been made from the dx x square minus y square orbital and has a fairly similar energy than the dx square minus y square orbital. So relatively little influence from the ligand group orbitals as well. Okay. So in good approximation, we can say that these orbitals here, okay, are our, well, valence molecular orbitals. Okay. We can say that these orbitals are, well, valence metal d orbitals under the influence of a square planar ligand field, okay, which is produced by the hydridoligands. Okay, so now that means also that these orbitals here are the most relevant to construct our band. Okay, so these ones are strongly bonding, and we will neglect them. And these are energetically very high, and we will neglect them as well. Rather than that, we will make our band diagram from those. Okay, that's of course a simplification, but a reasonable simplification, since the properties of a compound are always associated with its valence orbital. Okay. Now, let us construct our band diagram by combining the metal valence orbitals to form a one-dimensional chain. Okay. We can first start with the dz square orbitals. Okay. So the metal dz square orbitals interact in sigma fashion. Okay. Therefore, we would expect strong orbital overlap and a wide band. Okay. So now at k equal to 0, the algebraic signs of all these dz square orbitals are the same. Okay, and you see that this leads to the maximum bonding situation. Okay, therefore the most bonding crystal orbital will be found at k equal to 0. Okay, at k equal to pi over a, well, the algebraic sign of the dz square orbitals will be altered with every dz square orbital. That leads to the most interbonding situation, and therefore our crystal orbital at k equal to pi over a will be most interbonded and have the highest energy. So we'll have a dz square band which runs uphill and is of wide character. Okay, so now what about the dxz orbitals? So you see that the dxz orbitals, they overlap in a pi fashion. So at k equal to 0, we do not alternate the algebraic sign of the wave function. We see that this leads to the most interbonding interaction possible. at k equal to pi over a, we alternate the algebraic sign of the wave function with every other orbital in the chain. And you see that this now leads to the most bonding situation possible. Therefore, we have overall a band running downhill. Okay. Now this band will not be as wide as the dz square band because of the pi overlap is weaker than the sigma overlap. Okay, so we have our band running downhill. Okay. So now for the dyz, we have exactly the same situation because the only difference between the xz and the dyz is that the dyz is rotated by 90 degrees relative to the dxz, but like in the dxz, there is pi overlap between the dyz orbitals. Okay. Therefore, the band for the dyz runs exactly where the band for the dxz runs. Okay, it runs downhill and is relatively narrow. Okay. Now, what about the dxy? So the dxy orbitals, they overlap in delta fashion. See that here? And that overlap is even weaker than the sigma overlap. So in this case, the band runs uphill again, just because when we do not alternate the algebraic signs of the wave function at k equal to 0, the bonding interactions are being maximized. And when we alternate the wave function with every other d orbital, we maximize the interbonding interactions. But now our band is extremely narrow. Okay? Because the weak orbital overlap. So now what about the dx square minus y square? So now the dx square minus y square is rotated by 45 degrees relative to the dxy, but the dx square minus y square orbitals overlap also in delta fashion. Okay? Therefore, like for the dxy, we will expect, well, a band running uphill, but it's being very narrow. Now you see this band here, yeah, and you see that this band is energetically much higher than the band for the dx square minus y square. And that is because, as we see here, the dx square minus y square orbital is considered to be, well, interbonding, and therefore energetically considerably higher than the dxy here. All right. So last but not least, we could also consider, if you wanted, the the 6p orbitals that would overlap in a sigma fashion. So this will lead to a very wide band again because of the strong orbital overlap. So our band would run, in this case, downhill, because if you do not alter the algebraic signs, we could maximize the interbonding interactions. If you alternate the algebraic sign, we will create bonding interactions. So in fact, because of the width of the 6pz band is so wide, it actually crosses the very narrow dx square minus y square orbitals at higher k values. Okay. Therefore, this band is also of significance in the band structure, in addition to the bands for the d orbitals. Okay, so this would be this one here, right, above this one. Okay, so now we have to consider where our Fermi level is. Okay, and we can pretty easily determine this when we again look at our molecular orbital diagram. Okay, so we see that this orbital here, the A1G orbital, which resembles the DZ square orbital, is our highest occupied molecular orbital, and it's being completely full. Okay. Now, that means that basically all of our molecular orbitals, all of our crystal orbitals are being filled up to the crystal orbital, the DZ square crystal orbital, which has the highest energy. Okay, so this means that all these bands here would be filled in all these bands here underneath, also those that would resemble the platinum ligand singlet bonds, of course. Okay, but everything above would not be filled. So the dx square minus y square would not be filled, and the 6pz band would also not be filled. Okay. Now you see that, well, there's a band gap in between the completely filled 3dz square orbital and, well, the 6p z orbital. So this explains why our Krogmann salt is electrically insulating material. Okay. So we can also produce the DOS curves from the band diagram. So we have learned that a narrow band translates to a high energy density of states, while a wide band translates to a low energy density of states. Okay, so you see, for instance, that the dxy here translates to a very high energy density of states here, while the wide 3dz square band here translates to a very low density of states. Okay, the same in this region here. For instance, the dx square minus y square orbital translates to high density of states. The 6dz band translates here to a very low density states. Again, you can see that you have here a band gap. So up to this state here, the crystal orbitals are being filled. From here on, the crystal orbitals are unfilled, and you have a band gap, actually a wide band gap, that explains the insulating character. So now what changes as we go from the non-oxidized version to the oxidized version? Well, first of all, we change from an eclipsed orientation of the squares to a staggered one, as we go from eclipsed to staggered, the unit cell parameter doubles. Okay, so if the unit cell parameter doubles, because one unit cell would now contain 2 PTC and 4 units that are oriented in this staggered conformation, the band folds. Okay, so you see here the folded band for the eclipse conformation, and you see here the folded band for the staggered conformation. So you see that the difference between these are minimal. So the only difference is that when we go from eclipse to staggered, the delta bonds that exist between the dxy orbital and between the dx square minus y orbital goes away. Okay, so these orbitals become approximately non-bonding. So the bands that were originally already actually very narrow now become completely flat. Okay, so you see here the very narrow band for the dxy in the eclipse conformation. You see here that this band now becomes completely flat because the interactions between the dxy orbitals are entirely non-bonded. Okay, so now where is the Fermi level in the oxidized form of Krogmann's salt? So now we have removed electrons, and well, these electrons would be removed from the band which has the highest energy, which is the DC square band here. Okay, so while in the non-oxidized state, this band was completely full. Now the partially oxidized state, it's not completely full anymore. It's partially full. Okay, and a partially full valence band translates to metallic conductivity. And we would understand that this metallic conductivity occurs in the direction of the platinum chain, because the dz square orbitals point into the direction of the one-dimensional platinum chain. Okay, so this way we have not only explained the metallic conductivity, we also explained why the metallic conductivity occurs only in one direction. Okay, now we have discussed examples of one-dimensional extended solids. Now let's go from 1 dimensions to 2 dimensions. We can briefly start with that in the last 5 minutes. Yes, Tom, you have a question.
Yeah, I'm sorry, but you mentioned on the last slide or two, where is the Fermi level? I'm sorry if I missed it, but where is the Fermi level?
Where is the Fermi level? Okay. Let's go back.
Sorry, I should have asked that before you changed your.
So previously, the Fermi level was basically in between the dz square and the band for the 6pz orbital, right? So the dz square orbital was completely full, and the 6pz orbital was completely empty. Okay, but now some of the electrons are being removed from this band here, the 5dz square band. That makes this band now partially full. Okay.
Right.
Okay, and the Fermi level is somewhere within the dz square band. Okay, so approximately here, I can maybe just draw it in here. Here, yeah, qualitatively spoken.
Okay, so it's just somewhere in the band gap. That's all we're saying at this point.
Well, now it's not within the band gap. Okay, now it actually cuts a band.
Gotcha. Okay.
Previously, it was in the band gap. Now it's actually cutting the band. Because it's cutting the band, the compound becomes metallically conducting.
I see. Okay, now I got you. And that's why it's conductive. Okay. Thank you.
All right. Then let's move over to the next presentation, in which we now consider our considerations from one dimension to 2 dimensions. And like previously, we will start with a hypothetical 2-dimensional extended solid and then move over to a real-world 2-dimensional extended solid. So the most simple imaginable 2-dimensional extended solid would be a square lattice of hydrogens atoms. Yeah. So again, hydrogen is the most simple atom, having only the one s orbital. The valence orbitals, we arrange the hydrogen atoms in square lattice. That's the most simple 2-dimensional lattice we can imagine because it has the highest symmetry. Okay, so now what is different to the 1-dimensional case? The main difference is that we have now 2 k vectors, k1 and k2, that point into the 2 different dimensions, okay, x and y, okay, and these 2 k vectors, they form a lattice in the reciprocal space, and the reciprocal lattice, well, it's reciprocal to the square lattice in the real space. Okay, so now we can systematically vary kx pointing to x direction from 0 to pi over a, and we can do this independently for the k vector that points into y direction. All right. So now we can first look at the crystal orbital in which kx is equal to 0 and ky is equal to 0. So that means that we do not alternate the algebraic sign of the 1s orbitals in either direction. Okay? They're all remaining positive in both directions. So in a sense, that means that all the 1s orbitals in our associated crystal orbital will be having the same algebraic sign. It's intuitively clear that this crystal orbital will be completely bonding. Okay, we call the point at kx equal to 0, ky equal to 0 in the residual space the point lambda. Okay, so now we can, for instance, go to k x equal to pi over a and ky remaining 0. So this means that we now flip the algebraic sign of every other 1s orbital in k direction, but not in y direction. Okay, so you see that we get another crystal orbital here, and the bonding analysis of our crystal orbital would tell us that, well, now we have bonding interactions here in this direction, but we have anti-bonding interactions in the other direction. So overall, we would have an approximately non-bonding situation. Okay, now I just see we're over the time, and I will need considerably more time to explain this. So let's stop at this point. I will just restart with this slide in the next class then. So let us just stop the recording here.